Unusual observation, which is the outlier. When we have an outlier, that might affect our regression results significantly. This is the kind of extreme observation. Sometimes we have like a data, something like this, right? And then we have a one big data here because we trying to minimize our the mean square error. So your regression line may looks like this. The actual one should be this, right? So if you only because of this one point, actually your regression line will be totally off from the real regression. So you can find out the outlier and then you can take it out. Inferential observation is this is a kind of inferential operation. Even though this is the outlier, but if it's close to the line, this is so far from this mean, right? Far from this mean, it's far away. But if we keep drawing, so even though I included this point, our regression line doesn't change that much, right? Then that's not an influential observation. But this one is the influential observation. So we will see the leverage and the outlier. So you can talk about what is the leverage and outlier. Cox distance is you can calculate it, so you don't have to worry about it. Actually, you can use the R function, Cox distance, then you can actually find out. This is a measuring about effect of deleting. So if I delete that point, how much it will affect. So that's what we call this Cox distance. And then if you have that has a lot of the distance, big distance, considering really bigger than any other data point, then you have to consider the taking out that point. And then you see if that taking out that point improved your regression model or not. Outlier and leverage. Leverage is depends on we are looking at the independent variable. So independent variable is here. So these 2 points is outside of the range. So that's why we call. So outlier or the leverage is depends on are you looking at the dependent variable or independent variable? This is a deviate from dependent variable wise is away from the group. That's the leverage. And then if you take a look at the dependent variable side, this is the normal range of all the data, but this is far away from there. That's what we call this is outlier. But actually, this is like a high leverage and also the outlier. But actually, this is okay because, as I told you, this data point, even though you included this data point, my regression doesn't change that much. But these 2 points, if you add these 2 points, your regression curve will change significantly. Sometimes we use regression for the prediction. So we find out the relationship with X independent variable and the dependent variable, and then we find out the new observation coming in, and we trying to predict what would be the Y, what would be the independent variable. So once you find out the equation, the regression model, which is you find out all the B0, B1, B2, and BK, and you observe the new observation of X1, X2, X3 independent variable. Then using the formula, you can predict the Y. Okay, and then you can have a confidence interval for the mean of Y using this one. This is obviously the predicted one, but you can have a confidence interval. And also this is what we call the prediction interval, individual y. So whenever you individual y, I mean for the new things come in, new observation come in, without knowing y, you can predict, you can use a regression and then predict a value, y value, and then that prediction will have a confidence interval. Okay. So you don't have to worry about this formula because we are not calculating these things by hand. Again, we can use our formula and then you can simply find out the confidence interval of the mean y and confidence interval for the individual y. So this is how you calculate it. So this is again just variable. You don't have to use a dot. That doesn't mean anything. So if you do the linear model, this is y and this is x1. Using the data, you can do the this is a model, and then you can see the summary and you can see the what is the beta, what is intercept coefficient, what is r square, and so on. And there's the new data, which is speed is 30, so speed is x1. So new observation, I know speed is 30. Then what would be the distance, right? This is a distance against the speed. So y is distance equals b0 plus b1 x, which is the speed. So once you got a number, then what would be the distance when the speed is 30, right? So once you got a whole number, then you can estimate y value here. That's how you predict the function predict. This function is quite useful even when you do the machine learning. So it doesn't have to be the linear regression. You can use a support vector machine or the decision tree, whatever. You have to use this predict function. So model is coming in, but this case, our case, this is a linear regression model here. But you can have a SVM or decision tree or random forest, whatever, any machine learning model can come here. And new data is the new data. This is like a speed is 30. And then interval, you can set the option. Interval is a confidence interval. Then what you can get is it will give you the prediction, which is the y hat, and also we can have some kind of interval here. Because this is confidence, you will have a confidence interval. Same thing here, only option difference is the interval is a prediction, then you will have a prediction interval. We already seen some square things, and then I just mentioned we just consider the x square as a new variable. That's why this is still the linear regression. Dependent variable sometimes has a nonlinear relationship with the independent variable. So first thing you can try is the quadratic model, which is a square. So you can simply create the x square here and then treat it as a new variable. Still, this is like a linear regression in mathematically, but on contents-wise, this is not a linear model. So this is example. So marketing department of large supermarket chain trying to find out what is the price elasticity. So which means is price change, what the sales will change. Of course, what you can expect is a high price. You expect the sales goes down. So this department supermarket chain selected a 15 store. And then with the equal traffic, here the traffic is how many customers are coming in, and product placement is selected, and then 5 stores randomly assigned to each of the 3 price levels of package razor. So this package razor, you have a 3 different price, P1, P2, P3, and assigned the each 5 store, right? And altogether this is 15 store. So this is the data, store 1, 2, 3, 4, 5, 15. So this one number doesn't mean any quantity. This is just number 1 store, number 2 store, and so on. And apply the price is $80, $100, and $120. I don't know this is a dollar or exactly, but this is a sales data. So since we have only 3 different price, it's 80, 100, and 120. So that's why price is 80, 100, and 120. But if you plot the things, this is not completely linear. This is a more like this, right? So when you just plot the simple data, you can have an idea. Maybe this is not a linear relationship. This is more like a quadratic relationship. By looking at, you can just simply find out. You got an idea trying the x square, price square. So if we use just linear model, just using the price, and then what you can see is the R is like 88. It's pretty high. Of course, this linear has a, F is way smaller than 0.05. So we can tell this model obviously tell us something meaningful. And then the coefficient, p-value is already pretty small. So price is a significant has a significant effect on the sales. I can tell. However, if you plot the residual plot, so residual plot you can draw. This is the I draw using the Excel. But if you just choose the option in Excel, you can you can plot the residual plot. Obviously, this is not a linear. This is the residual plot. This is like this. Ideally, what should be the residual plot should be the pretty flat, right? This is the ideal residual plot. It doesn't have to have any pattern at all. But here, clearly you have this kind of pattern. Then you can get an idea. Yeah, I have to include the price square here. So if you include the price square, so I include the price square as a new variable. Now your R square is about 93%, right? The previous one was 88. Still, this is a significant, and then even price square is a significant, and price is also significant. Everything is fine. So clearly, this model is better than the previous one. Right now, if we plot the residual plot, this is still however, this is way better than the previous one. It's close to the flat residual. So obviously, this residual plot is better than the previous one.